Hello, everyone. Thanks for joining us today. We're going to give folks a couple minutes to join. While we wait, I was discussing my latest conspiracy theory at the mesoscale with Phil and Alden, which was the Ice Age caused by a meteor, or is that a little tendril of chaos of our weather system? I won't make this a poll. But and it's something I don't know that much about. Maybe there are some, prehistoric archaeologists who have seen the meteor that caused the volcanic activity. But Phil Alden, do you subscribe to my new conspiracy? Chaos conspiracy?
It's certainly an interesting one, and I hadn't personally heard it before, but yeah, I mean, there's a lot of possibilities out there, so curious to learn more about it.
Very professional non-answer. Thank you, Phil.
Yeah, right.
I wouldn't be surprised if it's all wrapped up in the other theories that we have about it, about volcanic activity, large meteor strikes. I wouldn't be surprised at all if that volcanic activity was also periodic and there's some feedback.
Yeah. We'll talk about weather forecast limits of predictability, but if anyone knows some volcanic, what's the hottest volcanic prediction model, definitely let us know. We'll need to use that as an input to predict the next ice age. All right, I think we're at a good critical mass of attendees, so I think we can get started. Just some table setting. This is being recorded, and we'll share a recording after. So if you have some colleagues that didn't attend or you have to hop off, you'll get that recording. We have a little, if you haven't been in a Zoom webinar by now, congratulations, but you're probably familiar with the Q&A feature. You can ask questions whenever, and if it kind of like lines up with the topic that we're talking about, we might jump on it, and then we'll hold some time at the end also to address them specifically. So feel free to sling them our way. So maybe just y'all could, Alden, Phil, you could see my screen, right? Okay, so I'll just start by introducing myself and Alden and Phil. So my name is Marshall Mounteau. I also go by Marsh. I'm the CEO and co-founder of Upstream Tech. We make river forecasts and also some remote sensing and remote monitoring software. I also co-founded an organization called dynamical.org, which was kind of born from the river forecasting work and the challenges of dealing with weather forecast and numerical weather prediction data. And that has really sparked this fascination personally, but also professionally, with chaos and chaotic system and limits of predictability. Recently, Alden and I started a podcast called Weathering. Check it out. We're finally ticking that tech bro box of having a podcast with our colleague Marta, and we were reviewing papers at the intersection of machine learning, AI, and weather, and data, data structures, computation, programming languages, whatever. And it's been a really fascinating topic area because it's so fast moving, and a lot of the things that are held on a pedestal in the space of weather are being challenged. So it's a really interesting time to be thinking about chaos and nonlinear systems and how AI is applied to those problems. So that sparked this topic. Alden, you want to introduce yourself?
Sure. Good to see you all. Meet any of you I haven't met before. I co-founded Upstream Tech and dynamical.org with Marshall, and I'm the CTO now of Upstream and get to do lots of fun engineering things at dynamical.org as well. So my day-to-day work is deep in the actual model building, machine learning, and then also thinking quite a bit about how we move data through the whole systems, and then how users can actually understand and interpret and take action based on the forecasts and data that we provide. And it's one of my, like, even outside of work, long-term life goals is to help people in the world understand and use probability and risk thinking more effectively. So when we started talking about this topic, I was very excited to jump in. Phil, I'll turn it over to you.
Excellent. Hey everyone, I'm Phil Butcher, engineer on the hydro forecast modeling team. My background is in weather and hydrology, so I've been at Upstream since 2020, working on designing and building models and getting models shipped to customers. And it's been an interesting time to like see the wide range of customers and use cases for forecasting and the different challenges that pop up with that. I've previously worked at Bonneville Power Administration and also the National Weather Service at a river forecast center. So I've been in this space of forecasting these chaotic systems for a while now. And actually, I think it's been about 15 years. So crazy how fast it goes. But yeah, excited to chat and see how this conversation goes.
Awesome. Thanks, y'all. And just because we'll talk about this a little bit later, I'm based in Nashville, Tennessee. Phil is based in the Pacific Northwest. Alden is based in upstate New York. And so our little regions have very different patterns of weather, very different hydrologies. And I think it's also interesting just as a distributed team to have a breadth of different hydrologies, forecasts that we're also looking at. So we'll talk a little bit about that later. But I just wanted to introduce the team. The team is awesome. I think one thing that's really helped us make a number of breakthroughs at the intersection of hydrology and machine learning is that we do have folks like Phil on the team that bring a background in hydrology. We have PhD hydrologists. We have folks with backgrounds in meteorology, water resource engineering, forestry, and then, of course, lots of software. And so all of that comes together, I think, to create a pretty unique perspective on how we can solve problems, try new things. So that's the team. And it was, of course, because we're extremely hip, shot on a disposable camera at our Nashville retreat. So I think today my goal is to talk a little bit about the limits of predictability, both in the context of weather, but also why it's different in hydrology and why we make the claim of going far past the limits of weather when we're doing river forecasts. We're going to talk a little bit about some of the history and also fast evolving landscape around determinism and ensembles and uncertainty, and then talk about seasonal 3, which is our latest model architecture that's trying all sorts of really cool stuff to tackle the challenges that are inherent in a long-term or annual or whatever you want to call it forecast. So that is where we're going to dive deep there, and hopefully I'll bring some questions as we go. So first up, limits of predictability. This might be old news for a lot of y'all, but in 1969, Lorenz, Fetter, and Hamilton, it usually gets credited just to Lorenz, but I'm making a habit of crediting the two collaborators Lorenz had. They did pretty groundbreaking work showing that small perturbations to initial conditions led to such different results in weather forecasting that the theoretical limit was 14 days. Like, no matter how good we got, 14 days, because of the nonlinear equations and how we had to solve them, like, good luck getting further than that. It's impossible. And since 1969, that has stayed the kind of gold standard limit of predictability, being cited in up to even many of the most recent AI or hybrid weather model academic papers published in Nature saying, oh, yep, 14 days is the limit. Before I talk about the one recent advance in that space, Alden, Phil, anything you want to talk about Lorenz, or anything you want to add there? Do you believe it? Do you believe 14 days is the limit?
Go ahead, Phil.
I mean, given my weather background and education, certainly that's what I was taught, and sort of widely believed for a long time. Yeah, this new paper that you're about to talk about certainly makes a compelling case. Maybe not 100% compelling, but like a pretty compelling case that that limit is like, quite possibly beyond that 14 days.
I think it's a really interesting example of how a like postulated theorem can grow and grow over time into like almost just an accepted fact / dogma, where people will just say like this is exactly what it is, and
the word limit I think helps with that.
Yeah.
Like, oh, it's a limit. It feels like a law.
There's a wall that you run into, and yet they didn't prove it. In fact, this would be incredibly difficult to prove. So I was tickled when this paper came out that Marcia's about to talk about.
Yeah, so I think so this is a paper called Testing the Limit of Atmospheric Predictability with a Machine Learning Weather Model. We got a whole podcast episode on this one if you want to check it out. But it's out of the University of Washington. Lots of really great papers coming out from this group. So I would just look at everything they've authored recently if you're interested in this space. But what they did was they took GraphCast and they actually back propagated error to the initial conditions. And Alden, if I'm fuzzy on anything, correct me. And they were showing that actually a lot of the limit is due to error in the initial conditions, not necessarily that the equations are limited in such a way that they can't predict further out. So it was pretty exciting. It did, like Alden said and Phil said, it didn't prove this, but it hinted at a possibility where the limit is much further out than 14 days. And they tested it with an additional AI weather forecast model just to remove a little bit of the, feedback loop of using GraphCast to feed the error back and then using GraphCast to feed it forward by using, was it ForecastNet? No.
Pangu Weather.
Pangu Weather, right.
Another AI weather forecasting model.
Yeah, and that didn't really show skill out past 14 days, but it did show improvement in skill in the shorter horizons. In any case, super compelling because as hydrology people, right, our interest is we're trying to make forecasts way further out than 14 days, right? 14 days is maybe like it's the end of short term for us and the beginning of something longer. And the limit has always been that the weather models are not so great out 90 days, right? They don't add skill to the model if there are even weather forecasts that we're going to incorporate out farther than, a couple weeks. So we're tracking this space closely because if there's anything, a breakthrough ensemble weather forecast, something that has longer range, whatever, we're tracking it very closely because we want to rapidly integrate that into any work that we're doing. So that's why this is so compelling to us. So I'm gonna hold. I always recommend books. This book is great. This is recommended by a listener of our podcast. It's called Chaos: Making a New Science by James Gleick, and it kind of circles around all of the figures in this era who were focusing on chaos and how chaos impacted predictability and kind of stability within systems. And this chapter focuses on specifically Mandelbrot, talking about rivers. So I was going to just reference this real quick before we talk about now how does hydrology specifically differ and what does it have in common with the limits of predictability of weather. So Mandelbrot turned to other data drawn from the world's rivers. Egyptians have kept records of the height of the Nile for millennia. So he claims that there's two effects common in economics as well. And Mandelbrot was this figure who jumped between disciplines and kind of like solved every problem, but was like never recognized in the moment as like solving every problem, but he pretty incredible figure. He calls them the Noah and the Joseph effect, which is, very biblical, but the Noah effect means discontinuity. When a quantity changes, it can change almost arbitrarily fast. And then jumping ahead, the Joseph effect means persistence. There came 7 years of great plenty throughout the land of Egypt, and there shall arise after them 7 years of famine, which is kind of funny that, the Bible has a seasonal forecast in there. Furthermore, mathematical analysis of the Nile's height showed that persistence applied over centuries as well as over decades. So check out this book. But I'm referencing that because that's actually a really important thing in how we've started to approach not just forecasting a season, but forecasting across seasons and looking back in a really flexible way intra-seasonally. And this is really important because I think it becomes a really hard problem if you're using conceptual models, but it's something that AI gives us this tool to be really flexible in terms of how we're using memory, how we're experimenting with variable lengths of memory, and how that can help track things that maybe aren't necessarily reflected in a weather forecast, but have incredible import to hydrology. So also, if you can name, if anyone can name some of the movies that I'm using pictures from, I'll send you a copy of the book. Alden got this one, which I was very surprised about. The main thing that separates hydrology and weather is that water has memory. And this is the main thing that we are exploiting in order to get seasonal forecasts that go out further into the future. So I think a way to illustrate this is that is back to where Alden, Phil, and I respectively live. So Phil, maybe you could start. Can you describe like what is the memory of your hydrology, and then Alden and I'll talk about mine.
Yeah. So here in Portland, when you look to the west, for example, you can see Mount Hood, and right now there's not much snow on it, but during the winter when you get a random day and it's not raining and you can see the snow, there's a lot of snow up on the mountain, and that snow has like a ton of information about like how much water is going to be in the river the coming summer. So the memory that the basins in this part of the country have is like the land itself is like storing information about what may happen in the future. And so it's really important to measure like what is on the ground right now so we can know what's going to happen, say 6 months from now. But I know, like say where Alden lives or you live, Marcia, things are very different than that.
Yeah. So Syracuse used to be, and you hear the stories of massive snow events, and it's snowy all summer, snowy all winter, and the drifts build up, and they don't disappear till April, maybe late April. Hope it's done by April. Now, more recently, the past couple of years have been pretty different. So we're kind of in an in-between state where there's at some times of the year, memory that's coming from a good amount of snow. The soil moisture absolutely is playing a big role throughout, but rain events that can come on very quickly, particularly in the summer, are a real factor. We get lots of convective storms, quick, small thunderstorms that are popping up. I was just thinking of, I was talking to a friend who lives about 30 minutes away, and they got dumped on yesterday, and we didn't get dumped on here. And I'm thinking about how that, the entire distance there is the length of 2 pixels from the GEFS forecast model. We're experiencing entirely different weather place to place in pretty small areas during those particular times of the year. And that reduces the amount of memory that we see in those more rainy, quick storms times of year.
Yeah, I mean, and Nashville and Tennessee more broadly in the Southeast talk about chaos. I have, sun showers are common in the spring and summer. I have a picture standing in very blue sky, but this one little finger was on me and it was raining on top of me. So I think that's there might be a little bit less memory, certainly not, snowpack and snowmelt here. And so what's interesting, I've been kind of glomming on to this analogy of hydrology, which also speaks to why we can, I think, forecast further into the future, where when you're training a weather forecast model, you really have one Earth, right? One Earth of observation, and everything that's happening on that Earth is influencing everything else because it's this like fluid dynamic system, et cetera, et cetera. But with hydrology, you almost have these little universes. And of course, weather is an input that, you have to think about globally. But these little universes are almost of hydrology, the watersheds, almost have an affordance around machine learning and having more historical record to train across a large diversity of hydrologies. And so there is a lot of diversity between those different universes, but it's as if we had, satellites around dozens of other planets that were Earth-like, and were able to observe like their ice ages and their weather patterns and use that as a way to understand the physics of the system better. So that's a really key piece of how we structure hydro forecast. Phil Alden, do you want to talk a little bit about that kind of core philosophy around the foundational core model that we train?
Sure. So like Marshall said, we take advantage of the fact that there are many, many different basins that we can learn from, and that the laws of physics, as far as we know, actually stay constant as we move between places and over time. And so where in many cases, if you think about a modeling problem, the domain you have to learn over is time. If we start shifting how we think, we can learn over time and we can learn over space. And that's important both just because more data allows statistical and AI-based models to learn more nuanced relationships how things work, but also because what's going on in those other river basins is truly often very different from what's going on in my particular river basin. And if my model has been able to learn from many, many basins, now it is required to actually learn this more general hydrology that is similar to how things are going to, that may include how things are going to be in this basin in the future. So in some way, we're able to substitute space for time, and in doing so, give our model a much broader understanding of how hydrology really works.
Maybe just jump in and put some like context around that. Like, with my hydrology background, like the world of hydrology, because every basin is so unique and so challenging, the typical way with, physical models or conceptual models was to train a specific model that was unique to every basin. And so you're sort of like limited in the broad applicability of those models because it just took so much time and effort to get them to work in each of the unique basins and hydrologies that happen. And I think the big breakthrough with machine learning and techniques like what we're using is that ability to learn all that stuff together at once in one model. It's been really exciting to see that transition over the past 5 to 10 years in hydrology.
Okay, I want to switch gears back to a little bit of history that tees up the next section of the talking about chaos and seasonal forecasting, which really centers on ensembles and uncertainty. So I'll get it out of the way that determinism was kind of debunked pretty quickly. I think it was Newton that was like, oh, if we have a perfect equation and perfect initial conditions, we can predict the universe. I still find that compelling, not necessarily as like an axiom like law, but as a challenge of like how much of uphill battle is chaos. Like, do we have enough are our initial conditions good enough? Is our mathematics the right mathematics to perfectly capture not just the macro but the micro? Yeah, but line through. So I think what people started looking at was, okay, if we can't perfectly predict everything, how can we represent uncertainty? There were a couple figures. I'm sure the list is much longer, but in the 60s, someone named Edward Epstein, who was inspired by Lorenz's work and started using Monte Carlo methods to study atmospheric predictability, and trying to interpret uncertainty as this kind of like glob of points following deterministic paths. And then Lorenz was like, that's cool, and started doing little ensembles of initial errors that reasonably estimated error growth. And then that came back to some other figures that started doing like ensembles and saying, oh, maybe if we take the mean across lots of different ensemble members, they can give us some useful signal. So all of this work was happening in the 60s and 70s. And what's cool is in 2025, we're on an ensemble renaissance because a lot of the AI weather models, their strength is like the headline strength you read on like a news website. Oh, weather model beats, blah, blah. That's all accuracy. What's not always frontline is they are so much more efficient computationally. And so we've seen this pivot, whether you're looking at DeepMind's GraphCast, NVIDIA's work, ECMWF, they're all pivoting to away from like a model that makes a forecast to these massively scalable ensemble models. And that's really, really exciting. So Alden, Phil, what do you like most about ensemble weather forecasts, and how do they help you think in terms of uncertainty, and how do they help a model downstream think about uncertainty?
What I really like about ensemble weather forecasts is that they give us a view of like the possibility of extremes that may happen. I think we all know with like a weather forecast, like, man, like, is that really crazy heat wave going to happen? Like, I know it's possible this time of year, or is that crazy rainstorm going to happen? And like you go look at a deterministic forecast and it either like has it or doesn't. But then you start looking at, say, an ensemble forecast, and you're like, well, okay, this thing has 30 ensemble members, but that one is like showing something funny. And you start watching that from model run to model run, and now say 3 ensemble members are showing it. And like it gives you this possibility that these rare events can happen, whereas a deterministic model is just a lot more binary information. So I think knowing that these possibilities exist are really important for like making decisions about like what you may do. Like, do I need to, operate a reservoir differently to possibly prepare for this really bad situation? Stuff like that.
Maybe I'll just add that I like that they're an honest acceptance of the fact that we don't know everything about the future and there is uncertainty. And here is one of our best approaches to address that and take that into account and then do what we can with that information. I also particularly, there's a number of different ways to talk about uncertainty, but I think there's something nice about an ensemble, meaning a number of different possible, distinct possibilities, a number of different traces in a larger ensemble that help us humans really actually grapple with and think about these possibilities. It's one thing to hear that there's a 5% chance. It's another to kind of see a real possibility, a real line on a graph somewhere saying like, this is something that has a chance of happening, this very specific sequence of events could really be something that we need to prepare for.
Awesome. And thank you, Vereen. Vereen just corrected / reminded me that it was Laplace that posited that perfect information could predict the universe. You're so right. Thank you. I'm surprised everyone didn't rage quit the webinar. Okay. So what we're looking at in terms of ensembles in weather, NOAA, GEFS, which we were all looking at the history of ensemble weather forecasts the other day, and we were like surprised at how long GEFS has been around. It's been a while. It was like the early 90s. Yeah, going strong.
And ECMWF was right there too. They made their first boat. 1992 was a big year for national weather agencies starting to make ensemble weather forecasts.
Yeah, so we kind of have these like gold standards that have, you know, been time tested. I don't know if that ECMWF in 92 is the IFS ensemble. That I think it was probably a precursor.
Exactly.
But we have some pretty well established physics, you know, numerical weather prediction ensemble models. They have mixed performance. And I think that's part of the reason why the ensembles are so useful. Actually, if you want to check it out, we created a little toy. I didn't plan to show this, but I'm going to show it really quickly. I was having trouble conceptualizing how an ensemble model's performance at the mean was comparing to so GEFS, how it was comparing to GFS, especially at the station level. So I knew maybe at the macro, like global statistics level. But what I was interested was, you know, in my chaotic Tennessee, you know, here's my airport. I wanted to see how is GEFS outperforming GFS. So this is a little toy we made. If you want to build an intuition for your place, we'll drop this in the chat. But it's cool. You can kind of just like click in and it automatically updates. You know, you could say, oh, I care about the last 14 days or the last 180 days and see how those statistics track. And as we add more stuff, this is, you know, a little bit of a tangent, but as we add more models here, you'll be able to quickly see, oh, how does ECMWF's forecasts stack up, or how does HERD work at the shorter horizons?
And if you're not in the US and you want to see,
we're adding that.
Send us an email.
Yeah, really the limiting factor there is just figuring out the best map projection for that, because I'm using Albert's whatever. Anyway, so but we alluded to this. There are these recent AI ensemble forecasts that one is built on ECMWF's AIFS. Google has some GenCast and FGN. There are NVIDIA is doing some. There's just like a whole corpus of new ensemble forecast models with the promise like, oh, you want 1,000 ensemble members? You're just limited by, you know, the GPUs you have that you could spin up. So this is really exciting because I think it kind of changes the game a little bit for how you might utilize ensembles and how, more importantly, you might represent uncertainty in the models. So how, you know, when people are looking at a physics-based numerical weather prediction, how are they perturbing that model to flow to the ensemble members? And how is that different from the AI models? How are they doing it differently?
This is still a pretty exciting area of research in the AI model world. Some models are adding noise, but it's very particularly structured learn noise to those initial conditions, and then at every single step of the forecast as well. That's roughly the approach that Google's current operational ensemble GenCast, or now it's called Weather Next Gen, takes. Then in other situations, they're actually perturbing the strength of the connections in the neural network itself in order to by training multiple different models. This is, you know, very similar to just like calibrating a whole bunch of different models, starting from slightly different places to end up with a suite of them. But then they're also doing that additional tweaks to those strengths of those connections just as you roll the model out over time. And I think what's exciting about all of these is that by using a machine learning approach, you can have the objective that the training algorithm is trying to maximize be the fit of the uncertainty distribution that's coming out of the model relative to to reality. And this is not something that's trivial to do when you're coming up with algorithms to modify initial conditions in a traditional numerical weather prediction model. That's like, it's much more of a try an approach and see how it works and go back and try another approach. Whereas with these AI approaches, we can actually say your objective is to make the best fit ensemble that you can, and the learning algorithm actually optimizes that.
So I think just we've been tiptoeing around the hydrology a little bit. When we're talking about our latest seasonal forecast, which we'll talk about in a second, but how are we representing uncertainty, and how do these weather forecast traces, how are we utilizing them in order to create like our downstream ensemble of traces that folks can look at?
Yeah, I can jump in here on this one. So, so from each of, these ensemble members from different weather sources, we feed those through our models, which have, and as Alden said, our models, machine learning models. So it's like it's learned. We're not necessarily learning just the streamflow output, but we're learning the parameters of a mixture distribution. And when we tune that model, we can optimize it to have well calibrated confidence bounds. So we have that model, and then we're feeding weather ensembles through this model to give us ranges of possibilities. But each of those traces that goes through each of those have their own uncertainty. So then we're combining the uncertainty from all these possibilities together into our kind of final kind of uncertainty forecast. So a lot of times what I've seen in like other, stream flow uncertainty approaches is you capture like the weather input uncertainty, but you don't necessarily capture the other aspects of uncertainty, which are the model itself, the observational data. So our model is really trying to kind of capture all modes of uncertainty and make use of all information available. Yeah.
And I think that's pretty exciting, because what it allows us to do is we functionally under the hood have a seasonal forecast where we're able to have different flavors forced by different things. So we have one that's actually looking at similarity years across Era 5 land and using that to create some traces. We then have the GEFS ensemble members run through, which creates traces. And like Phil said, just to make sure it's extra clear, each of those outputs has confidence and uncertainty associated with it. So you're kind of getting this like ensemble of probability distributions, not just, when I hear the word trace, I think of like a single line. And so we don't necessarily expect every user to like get into that level of detail of like using many members of an ensemble, each with their own confidence interval. But what I do think it lets us do is really recognize that each organization is trying to make unique sets of decisions. I think this goes back to, and I'll show this slide, which totally bucks my stylistic integrity, but is a really helpful visualization. What it goes back to is like our different hydrologies, I think in a way are an analogy for the different kinds of risk tolerances, environmental factors, organizational priorities of different regions, but also different companies, and how uncertainty is going to be used in completely different ways depending on the organization. We might have a shipping company using river level forecasts on a major river that needs to make certain determinations about thresholds that mean this lock is going to be closed, or a high flow event is happening, which creates an upcharge on shipping commodities. That's going to be its own set of how you take uncertainty and confidence and design a protocol around how to act using a forecast. In hydropower, you have, I say this a lot, and I'm sure most of you on this call know this better than I do, since I see a lot of familiar hydropower names, but it seems to me like one of the hardest multi-objective optimization problems I've seen, where you have so many different factors, so many different requirements. You're trying to make money in some cases, but also, adhere to this long list of other things. And so that's why each organization needs to look at their risk tolerance and their objective and decide, okay, let's do this off of the upper 90% confidence interval, and these on the mean. You're right, for these lead times, right? It needs to be a very collaborative and integrated process to really design these protocols. So I think that's one of the things that's most exciting about having really rigorous uncertainty incorporated from the get-go and leveraging more of these ensemble inputs, is it creates the best representation of uncertainty. That means that an organization then can purpose fit a process for how are we going to use this for this specific decision. If you just had the mean or a bunch of ensemble traces, it might be difficult until you dig into exactly what's being perturbed, or like how that reflects actual reality of uncertainty in the distribution. Alden, Phil, anything you'd add?
I think probably the thing I'm most excited about seasonal 3 is how we have both set it up to make sure we're accounting for the various sources of uncertainty in its current form, and then made it be an open platform to continue to integrate this pretty clear trend of new ensemble weather forecasts that are almost certainly just going to continue to come out and be improved. And while at the same time having a process to sum it all up, so that on the days when the decision is not that difficult or not that complicated, there's one simple answer you can reach for, and we'll provide that too as well, if it's not one of those situations where you really want to dig super deep down and get into all of the component pieces that went into it.
Yeah, that's right. Or go ahead, Phil.
Yeah, I was just going to iterate how excited that I am about the framework of being able to kind of make use of new sources of inputs, basically, for these models. I've in my history of building models, I've seen model development take like multiple years, and I've seen that pace of development increase. And just being able to adapt and build models very fast to be able to capture and get the best information into users' hands as soon as possible, I think is what's most exciting to me, because it can be tricky to wrangle new data sets and figure out how to make models use them. And having something that does that is really, really exciting, I think.
Yeah, we're trying to get the best of both worlds, where we are gaining information for every incremental new input we're adding, but also the ability to very modularly separate them, so that we can iterate. And I think something we've done in the past was train like one mega model, right? It sees all the inputs at once. And there were a lot of benefits for that, especially at the short term. But we're seeing at the seasonal scale, it's been really helpful to modularize it, have that summing up, but actually have it be something where we can experiment a little bit more independently with this approach over here, that then gets folded into the kind of the choir. So that's been a really helpful approach. So here's my it's tilt shifted so that, it's advanced and cutting edge. I just wanted to make a cool screenshot. So let's maybe dig in for a few minutes, and then we'll get to Q&A into seasonal 3 and some of the specific major architectural decisions that we haven't talked about, and what Alden, Phil, you two are most excited about in terms of where we think this is going to improve what at the end of the day people care about, which is like accuracy of the main output.
Well, I'll jump in first. I think as a big overarching thing, I think we've said this before, but the key thing about seasonal 3 is it's really designed to explicitly account for and then help us work with uncertainty coming from many, many different sources, both in data, in model, in ground observations and inputs and outputs, the whole gamut there. One thing we haven't talked quite as much about is time. How does time fit into the questions of uncertainty, particularly because with streamflow, like many other things in the real world, there's autocorrelation. So yesterday's value is related to today's value, but not 100%. It won't tell you everything about today's value. And the result of that is that if you have probability distributions for yesterday and today, it's not totally trivial to just entirely combine them up together and get one single output. For if you have been users of our previous version of our seasonal model, you'll know that it ran at a 10-day step during the forecast period, and then really produced distributions at each of those steps. Those are, like I mentioned, not as easy to slice and dice and to get the exact period of time that you care about and then describe the uncertainty. If we have a bunch of ensemble traces like we have with seasonal 3, now we can actually say, I'm interested in Monday through Friday next week, but what I really care about is the total output during those weekdays. Now we can add all those up, those streamflow traces all together, and then you have a probability distribution that's well fit for that total quantity, taking into account that there's going to be a lot of autocorrelation, but not 100% autocorrelation between those different days.
Maybe if I could jump in. So Alden, you mentioned the time dependency, and that this is now going to 1 day time step and accounting for this autocorrelation. There's also the spatial correlation, and this model is we're going to a finer spatial resolution, but this does introduce this challenge of your upper basin. If you want to predict like a rare low probability of event, like you can't have all your individual components all saying like this is like the 99th percentile, because you route all that flow downstream and like you would just get a very unrealistic thing. So it's generally more likely that like one basin gets hit very heavy, a nearby basin doesn't get quite as heavy, and so there's like variability amongst the basins. So that's another component that we're accounting for and focused on representing accurately in seasonal 3.
Go ahead, Alden.
We talked a bit earlier in the about memory and how hydrologic memory and how that's actually really very valuable for us. In this model, we use a single long short-term memory LSTM block for every single subbasin. They actually happen to share their weights, so they know the same principles of hydrology, but they can see different inputs, including different characteristics of each of those basins, and therefore make different predictions coming from them. But that one really long, that one single LSTM allows us to extend that history of context that we give to the model about prior conditions in the basin leading up to the forecast time as far back as we want. And we've in many basins, about a year is sufficient to really capture the initial conditions necessary for stream flow forecasting out at a seasonal scale, but not every basin. And we've had some interesting cases as we've been working on this where we actually find there's locations where we continue to get improved in performance if we extend that history out to 2 to 3, even 4 years in the past. These are really interesting hydrology conditions like prairie hydrology, where there's these pock-hole, very small lakes that collect water and then really slowly allow it to then flow through the system. And because this one single, it's very simple in structure, but this single LSTM that's running at each of these sub catchments is able to learn those long-term time dependencies in ways that some of the actually more complex previous architectures that we used weren't able to pick up the nuances quite as well.
Yeah, and we expect back to, my region of Tennessee or the Midwest, we've had strong seasonal performance in snow-driven basins for a long time. And what's elusive has been skill further out, right? We've had reasonable skill at like a 90 day, sometimes a little bit further in the more chaotic places like Tennessee. But I think this has been really exciting for us because it's capturing some of those other water has memory things, like, these strange little lakes, or like the really moist soil, or groundwater influenced effects. So that's been really exciting to see as our accuracy keeps ticking up as we do more experiments. So maybe we could switch gears to a couple questions, which I think fold into talking about seasonal 3. So one is, are there any I'll repeat it faithfully. You were talking about the ability to easily integrate new inputs. Are there any that you are particularly excited about exploring and possibly integrated into this model?
I can just jump in really quick. As you know, the big breakthroughs in weather going on right now are these AI weather models, and there's a blast of them coming out, and they're evolving and changing every day. So getting those into our modeling framework and testing how they work for hydrology problems is what we are doing, and really excited about extracting the value of what's happening in the weather world and getting it into the hydrology world.
One thing we didn't talk about is that when you have an AI weather forecast, whether it's an ensemble one or just like a single output, compared to a physics-based numerical weather prediction, the thing that's also really exciting is the kinds of error that they're expressing is different. Do y'all want to just say like a word at how that helps us as downstream consumers have that kind of like diversity in input?
Yeah, so I mean, it really comes back to different processes for getting to an answer or getting to some prediction. If the same person told me 2 forecasts and they were both the same, I would not give that nearly as much weight as if 2 entirely different people who had never talked before and came from completely different backgrounds gave me a forecast of what would happen, and those forecasts aligned. So this is the analogous to that, where we have these numerical weather prediction models. Often every single ensemble member from a single numeric weather prediction model, they'll be wrong all kind of in the same way. As we get more diversity as you get, to go to another agency's numerical weather prediction model, you start to get divergences there. But as we go to entirely different approaches for even building models, we just increase the diversity of processes which we can actually get answers out, and therefore are better exploring the uncertainty space and going to get a distribution of inputs in terms of weather forecast to our model that are just going to cover the possibilities better.
More better. Alden, Phil, any other inputs that you're excited about integrating?
We're experimenting with some new snow data sets, both as additional outputs to improve the strength of the snow modeling processes in our models. We've seen some pretty exciting results on that. And this is just another example of more sources of data, even if they tell you complementary things, can be really valuable in making learning more robust internal representations in deep learning models.
Yeah. Another thing for seasonal models. So when you get beyond like the predictability of weather forecasts, it's very common for people to use analog forecasts, which are these like, historical inputs that you run through to see like what could happen in my basin. There's also like weather scenario generators out there, which are really good statistical representations of like what can happen in this basin that have, the temporal spatial correlations correct. But you can run thousands of them to get like, that event that happened like 5,000 years ago that's like really intense. Like you're not really going to capture that with analog forecasts where you have like, a 20-year history of what's happened. So incorporating these like other kind of inputs like that to get like really like how intense could things get in the space, or how dry could things get. I'm excited to have those in there too.
Yeah, my Ice Age simulator, back to the beginning. No, I think that's right. I think one thing that's cool too is that we can run the model arbitrarily forward. So we have some organizations that, recognizing the limits of predictability, want something that goes out 5, 10 years in order just to have something to base organizational decisions on. And what's cool is we could look at inputs that resemble more scenarios and force them through the model in a way that represents, okay, this is, in these scenarios, this is what's going to happen hydrologically, like what Phil is saying. We have one question. Do you have the sense of how different stakeholders are interpreting uncertainty? Do they understand the ramifications of it? Do they still think the mean is the best representation, or are they incorporating the uncertainty into their decision making? I think that's an excellent question. And I think I see a lot of hydropower people. I think hydropower folks are typically very sophisticated in this kind of line of thinking, just because of the ramifications of like critical infrastructure operations and the decisions of not just that, but the power that they produce, right? It's this nexus of criticality. I don't know if that's a word. And so where we see the most sophistication is in certain sectors where they have like a long history of thinking about uncertainty and risk. I think there are other sectors where they're water dependent, but not as sophisticated, and definitely not thinking about uncertainty. Maybe they're not even really using forecasts in a particularly sophisticated way. We see a lot of organizations say, oh yeah, we only look 2 days out, and beyond that, we think it's garbage, right? So I think that it's a pretty wide range, but where you're going to find probably the most sophisticated users are in hydropower. And as you move away to that, to kind of like other ancillary industries dependent on water or working on water, it's a pretty wide range of familiarity and kind of sophistication there. We see energy traders, and kind of anytime there's a lot of money to make, generally they'll think in terms of uncertainty too. I think we have time for one last question. If you're providing multiple years to initialize a subbasin's LSTM, does that mean the test period for developing the model gets extended further back so that you're not getting training data in the test period? If so, has that presented issues with having to reduce the training set or push it further back to the past so it doesn't represent recent conditions as well? Great question.
Absolutely. You are 100% right, Green. This doesn't necessarily, we have to effectively lose more data that's in the buffer period between our training and our test period. We've been lucky in a couple of these really tricky cases where they have had multi-decadal histories of observations, but it's absolutely a trade-off that there's not one great answer to get around You can definitely do k-fold training, model training, and validations. But again, with that, you of course have to be careful to make sure you don't have any leakage, even in your warm-up period.
And last question. Would there be a way to mesh the weather scenario generators with the forecast so users could generate arbitrary forecast traces? Ooh, that's cool.
That is very cool. Yeah, like we definitely want all these in the same model, but yeah, meshing them together. Definitely a good idea.
All right, Phil has committed. We're doing it. Awesome. We're at time. Thanks. Wow, almost everyone stuck around. So thanks for hanging out and talking chaos and seasonal forecasting with us. No one guessed the movies. It was Pi, which is slightly disturbing, but all about chaos and prediction. The one with the mountain was Train Spotting, not related to, well, very chaotic, but not related to chaos and predictability at all. No one guessed. So if you want a copy of Chaos, just message me. I have a couple of extra ones. Cool. Well, thank you very much. And we'll follow up with the recording, and we appreciate everyone joining. Have a good week.